Hi everybody. I thought as a follow-up to the project I did on the function generator, it might be useful to just do a short video covering off some changes and modifications I've made to that project to improve its functionality. And I must say that this has been a result of some very good feedback I've had from some of the viewers on my YouTube channel, so thanks to them. And let's go through some of these changes I've made now. Just like to point out a few words of caution. Quite rightly, one of my viewers pointed out that the power supply, the switch mode power supply that I'm using here, the connector block there is actually exposed even though it's recessed. So it can be quite dangerous, especially where you've got the mains input connections on that side there. So what I suggest you do if you use this type of unit, then you need to shield this really, and I've made a little plastic shield, cut it out of some plastic lid with a hole on one side. That then slots in there. Well, there you are, the plastic shield has been fitted. As you can see, it's bolted there at the side with a plastic nut and bolt. Conveniently, there was actually a hole in the metal casing of this switch mode power supply, which is suitable for doing just this. Now, just one other point might be worth bearing in mind is the mains cable coming out of the unit. You really want to have some sort of cable tie there to stop it being pulled. You can either use something like this, a clip which you can then screw and fix onto the plastic base with a nut and bolt, or alternatively you could use a cable tie. Well, there you see the cable tie now tightly fixed onto the mains cable. I've just trimmed off the excess, and if you simply now just drill a hole through the back cover, the cable tie will keep the mains cable from being pulled through. Right, for those people that still don't feel too comfortable working with this type of a switch mode power supply, where the terminal block is certainly exposed, then what I suggest you do, instead of purchasing one of these, for the same cost virtually, you can buy an enclosed unit like this. This is a 12 volt 5 amp DC power supply. It's fully enclosed, and you have the mains input socket on the side there, and on the other side you have the cable coming out, which you can shorten and then feed this 12 volt supply then to the main printed circuit board. The nice thing about this module is the size. It's a lot smaller, and it could actually take up virtually half the space of the other switch mode power supply, and then you just need to cut a hole at the side so you have access for the mains connector. So that's an option you have. If you didn't like the idea of using this unit, you can use one of these. This particular power supply module is from www.powerpacks.co.uk. You'll also find them advertising this on eBay as well, so you can either go directly or go to the eBay website. Another point that I'd like to illustrate is following some feedback I had from Henrik on this project. He pointed out quite rightly that on the output stage, on the input to the op amp that's taking the square wave signal, I had a capacitor isolating the input to that positive input of the op amp, and his question was, where does the input current bias go? Now, what actually happens in this case is the bias current is effectively still going through that capacitor. The capacitor charges up, so you do get some current flowing through, but it's not ideal. And what tends to happen is that the output signal on pin 1 here, instead of being centered on a 0 voltage, you find it's pushed down. So you'll see that there's more negative part of the signal than a positive part of the signal. I'll illustrate that on the oscilloscope, and we'll look at ways of how we can solve that. Now, one easy way to solve the question of the input current bias is to ensure that the positive terminal of the op amp has got a return path to ground. So you could simply fit a resistor from there, from the positive input down to the ground there, and that should solve the problem. But I just want to illustrate some issues with regarding that when we do it in practice, and we'll have a look on the oscilloscope. Okay, here we have the oscilloscope. It's set to DC input, so we're looking at DC voltage in, and the center line at the moment there is the 0, so going above that is positive and below that is negative. So the ideal solution would be for our signal on the output to go positive and negative by equal amounts. Well, let me just show you what actually happens when I connect the oscilloscope to the unit here. Right, well, you see on the sine wave there is the center line there, and you see it's going positive and negative by more or less equal amounts. It's slightly out on the sine wave, and I'll just explain the reasons behind that a little bit later. But that's not looking too bad. If I now switch to the square wave signal, watch what happens. You can now clearly see that the square wave signal is being forced down. There is the 0 line, so we've got 1 volt above the 0, and we've got 4 volts negative, so it's non-symmetrical. And that's actually caused by the fact that we have that blocking capacitor there on the input to the op amp for the square wave input, and it's causing this offset. Now, as I said, one thing we could do is put a resistor from the positive terminal of the op amp to the ground, and that should solve the problem. But the thing to be careful of is the value of the resistor, because it does have an effect on the signal and on the waveform positioning. So to illustrate that, instead of putting a fixed resistor from the positive to the ground, I'm going to put a variable resistor in and just show you what happens when I alter the resistance. You can see the square wave, the 0 line is there, so you can clearly see we've got 1 volt going above and 4 volts going below on the square wave. And what I've done, I've connected a 1 megohm variable resistor across from the positive terminal of the op amp to the virtual ground that we use. But I've also put a 1k resistor in series with it because I don't want to short it out altogether. So I've got the 1k in series with the 1 meg, so the minimum resistance will be 1k and the maximum would be 1 meg. Let me just connect the potentiometer and look what happens to the waveform. I've set it to maximum resistance, so 1 megohm in series with the 1k. It's connected. Nothing appears to be happening at the moment, and as I adjust the potentiometer, that's the 0 line there, so just look at how the signal is changing. So I'll now reduce the value of the resistance. As I turn it down, you can see now I'm shifting the square wave up, and at that point there we're more or less symmetrical. So there's the 0 line, and we've got equal amounts going positive to negative. If I continue to reduce the resistance even further, look what happens. We get distortion of the waveform. So going too low, we get distortion. What I've found in practice is that the best value resistance to use is about a 47k resistor, or anywhere near up to 100k, but I found 47k is about right. So what I'll now do is I'll disconnect the potentiometer and I'll put a fixed 47k resistor in its place, and we'll see what effect that has. Right, okay, that's with no resistor connected, so you can see here we've got the offset there, and just watch what happens to the waveform when I connect now the 47k ohm resistor. And as you can see, the waveform's now moved up, and it's centralized itself with regard to 0. So we've got equal amounts of positive and negative on the signal there. If I change the frequency, it holds it fairly constant. Right, well, as you can see here, the square wave now looks to be fine. Certainly is okay on all the higher frequency ranges. Now the only problem you have with what I've done is when I go now to the lower frequency. So if I flick the switch to the lower frequency range, and now what you start to see is some distortion on the square wave. You see here we've got some ramping on the top and the bottom of the square wave. And to solve that, we now have to adjust the value of the capacitor on the input to the op amp. We had a 0.22 microfarad. I'm going to have to increase that now to overcome this problem at low frequencies. So what I'm going to do is put a 10 microfarad capacitor in place of the 0.22 on the op amp for the square wave input, and let's just see what effect that has. There we are. I've increased the value of the capacitor there now to 10 microfarad, and as you can see it's cleaned up the square wave. So the lower frequency ranges now seems to be okay without any distortion. Well, that's the square wave signal, which looks now perfect. If I now switch to the sine wave signal, what you see has happened there is that it's not quite perfect. The zero line is there, and we've got slightly more going negative than we have going positive. Not a great deal, but it is slightly out. And the reason behind this is due to the input offset of the op amp, and what we should do, because all op amps do vary slightly, is trim the input offset voltage to balance out this error. Now one way I can solve this issue is to feed some bias voltage to the op amp that's dealing with the sine wave, so we can put an additional bias voltage to alter the input offset and compensate for this. We could simply do that by using a potential divider across the AT supply, then tapping off at the slider and feeding it onto the op amp. Or alternatively, we can do what we just did with the square wave op amp, and that is we can put in a capacitor to block the DC going into the op amp so the signal still passes through, and then put another 47 k ohm resistor down to the virtual ground, and that should do exactly the same as we had with the square wave signal, and that should then centralize the waveform. So let me just do that and come back. We'll see what the effect is. Here you can see on the oscilloscope the sine wave after I fitted that capacitor. I'm just pointing out where the zero line is. You can see we've got a small amount of DC of the signal above the zero, and all the rest is going negative. And what I'll do now is I'll put that resistor in from the positive input to ground, as we did with the other op amp. So I'll put another 47k in here, and that should then lift that sine wave up. There we are. So the 47k is in. So now if we look, the centre there is the zero, and we've got exactly equal positive and negative of the signal, so it's symmetrical. Right, we now see that if I switch between the square wave and the sine wave, the signal remains constant, centered around the zero line, so that's working fine. So just to recap on the modifications we made there to the input circuitry of the op amps. The square wave input now, we have a 10 microfarad capacitor feeding the input, and that was to overcome the distortion of the square wave at low frequencies. And take note there that the positive terminal of the electrolytic goes to the plus pin 3 of the op amp. And then we have our 47k resistor down to the virtual ground there. And on the sine wave input we added a 0.22 capacitor on the input, and again we put a 47k resistor from the positive input of the op amp to the virtual ground. And this modification seems to work quite well. It overcomes the problems we had where the zero voltage of our output signal was one-sided. It's balanced the whole circuit and it's now working quite nicely. Well, the next thing we're going to have a look at is the overshoot we can see on the square wave. You can see we've got some overshoot there on the leading edge and on the falling edge. If I just switch the scope out, we can look at that. So there you can clearly see we have a little bit of overshoot on our square wave signal. Now, an easy way to overcome this problem is to put a small value capacitor in parallel with the feedback resistor in the op amp, which affects the gain. So that in our case it's across that 20k preset in the square wave op amp. So we put a small value capacitor, probably somewhere between 100 pf to 22 pf or something like that. So let me just try and put a small capacitor across there and just look at the effect. I'll just put a 100 pf capacitor across there, and you can see quite clearly, I'm just holding it across, it dampens down the overshoot. I'll just try a higher value, you'll see what effect it has. This is a 220 puff, and you can see there that's too much, it's just taking it too far the other way. So it's a little compromise, this, and I'm finding that probably around about 100 pf capacitor is sufficient to reduce that overshoot sufficiently enough, and so it doesn't affect the whole range. So I think I've now soldered the 100 pf capacitor across the little trimmer pot on the feedback of the op amp for the square wave circuit there, and there you can see that it's clearly reduced the ringing that we were getting before on the rising edge. So I'll just switch the, and you can see now it's much better on both the leading and the falling edge. I'll just check it over the frequency range. It seems to be fine. So I think that's another nice little modification. 100 pf capacitor in that feedback loop seems to work fine. So just to recap there, I put a 100 picofarad capacitor across the feedback resistor there, that 20k preset in the square wave op amp circuitry, and that certainly solves the problem we had of the overshoot on the leading and the falling edge of the square wave. Well, I'll add all these little modifications onto the circuit diagram, and I'll give you a link to the revised circuit down below so you can print off a copy of the latest version. Well, I hope you found this video on the enhancements and modifications to our function generator project of interest. I will be covering the other features in a separate video, which will be the pulse output and also the option to use the function generator as an external frequency counter. But for now, thanks for watching. If you found this of interest, please give me a thumbs up, and I'll see you all again next time. Bye for now.